We're going to begin talking about the second form of rational functions. We talked last time in the previous video about functions that were the form of a over b onto x minus h plus k. And so we want to talk about what happens when we have a function of x divided by a function of x. And so there's a couple of different things we have to find with these, the first of which is a vertical asymptote or a point of discontinuity. So we know from the previous thing we just talked about that vertical asymptotes happen when the denominator is 0. Points of discontinuity happen when the denominator's got a factor that is also shared by the numerator. All right, so what we're going to do, the very first step in doing anything with these is to factor. All right, so we're going to factor first. And what happens is then if anything cancels out, so if there's a factor that the numerator and denominator share, then that becomes a point of discontinuity. All right, if there isn't one, then whatever else is on the bottom, whatever the other factors are that are on the bottom, become the vertical asymptotes. All right, and then we are done. So that's sort of the step-by-step process. Now we'll do an example so you can kind of see how this works. But basically what you're going to do is factor. Anything that cancels is a point of discontinuity. Anything that does not is a vertical asymptote on the bottom. All right, on the top, anything that doesn't cancel on the top is an x-intercept. All right, and then we want to take the horizontal asymptote. Okay, so to find the horizontal asymptote, we just look at the infinite limit. And you might be wondering what in the world is the infinite limit. I'll show you a quick way of finding the horizontal asymptote, and it's doing this but with a shortcut, so it'll make a little more sense, or it's a little quicker to do. But we want to find that horizontal asymptote. So these still have a vertical asymptote, they still have a horizontal asymptote. Sometimes they have more than one vertical asymptote, and then they also have points of discontinuity. So sometimes you have a point of discontinuity, a vertical asymptote, or maybe two, and a horizontal asymptote. So there's a bunch of different possibilities for these. And then the domain and range, it's similar with the range is, the domain is to what we were doing before. So the domain before was x belongs to real numbers, x can't be our h value. Now we say x can't be any value of any of the vertical asymptotes or points of discontinuity. And the range gets a little tricky. And so if we can, we're going to determine it from the graph, but if we can't, then we just don't state it. All right, and I'll explain that a little further when we get through an example or two, so you can kind of see how this works. All right, so let's go through an example, and we'll kind of refer back to what I said here, but those are the steps. So here's an example. It says x squared minus 5x plus 6 divided by x minus 3. So the first thing we do is we factor everything. The top is a quadratic, so it factors as x squared minus 5x plus 6 becoming x minus 3, x minus 2. And the bottom is just a single term. It's x minus 3, so it doesn't really factor. It just continues to be there. And then we look and we say, okay, what is on the bottom and the top? Is there any common factor? And there is. All right, there's 1, and it's x minus 3. So that means that the point of discontinuity is at x equals 3. All right. Now, you might be wondering, how do I know it's at 3 and 1? So what we do with that is we just find the y value by replacing the x value in everything else. So what I mean by that is, and I don't know if I have it written down here or not, I think I do, yeah, there we go. We cancel the x minus 3's, so we're left with x minus 2, that's the only thing that's left, and we plug our value, our x value, into that. So we go 3 minus 2, and that's 1. So that becomes our point of discontinuity, all right? So there's a point of discontinuity at 3 and 1, and because that's the only thing on the bottom, there is no vertical asymptote. Okay. Then we look at the horizontal asymptote. All right, and now to do this, all you do is you look at the highest power of x, all right? So the highest power, or the biggest degree, is 2, and you divide everything by that x squared. Okay, that's all you do. So you divide everything by x squared. And what that does is it makes everything either divided by infinity, if we let x go to infinity here. So anything that's over x or x squared goes away. But we basically just end up with our answer here with the constant term. So anything that doesn't have an x in it sticks around. It's 1 divided by 0. We say you can't divide by 0, so we leave it. We say it doesn't exist. There's no horizontal asymptote. All right? Now you might be wondering, well, how do I figure that out without knowing how to do limits? Because we haven't talked about limits. And basically, there's no horizontal asymptote. The degree of the numerator is larger than the degree of the denominator. So if you look at this, x squared is bigger than x, so that means there's no horizontal asymptote. Okay. Then we look at the x and y intercepts. So the x-intercepts, I told you before, come from the denominator and numerator being factored and then canceling anything that cancels. So we already did that with x minus 3. So what's left is x minus 2. Okay, and so that is our x-intercept. Our x-intercept is 2. So we have an x-intercept of 2, 0. Our y-intercept, we just plug plug x in as 0 and see what happens. And so we get just these cancel, right? Again, so we get 0, minus 2. So our y-intercept is 0 and minus 2. So we have all the information we want to graph this thing now. Okay, so what we have is we have our x-intercept at 2. We have our y-intercept at minus 2. We have our point of discontinuity at 3 and 1. So what we do is we draw an open circle there. So we're saying we can't be at that point, but it's just a hole in the function. And then all you do is connect the dots, essentially. So this is actually linear. It's x minus 2. That's what's left over. So you just draw a line through it. Okay, and then we state our domain and range. So our domain is going to be x can't be 3 because that's the thing that was on the bottom. And our range, we can notice, is just y is not going to be 1. And the reason I said from the graph is because if you look at this, there's only one place where it can't be, and it's at 1. Because there's a hole there. Okay, so that's the idea. That's how you find everything. All right, let's look at another example. It's a little more interesting. Okay, so we get x squared minus 2x divided by 4 minus 2x. So we factor out on the top an x and on the bottom a minus 2, and we're left with this. Okay, so we look first of all at what is on the bottom and see if it cancels. It does in this case. So we have one point of discontinuity, and it's x equals 2, and then we plug in, excuse me, to y. We plug in to this, all right, because those are now canceled out. And you can actually, if you want to, they do impact the initial conditions. So x can't be 2, but after that, they really don't impact anything. So anything that cancels, we can just sort of ignore it. Look what happens with the rest of the function. So we plug in 2 into what's left. That's where I'm getting 2 divided by minus 2, and that gives me minus 1. So there's a point of discontinuity at 2 and minus 1, and there's a vertical asymptote nowhere else because there's no other factor on the bottom. Okay? If there was, then we would have to look at that as a vertical asymptote, and we'll look at an example in a second that has that. And then we said the degree of the numerator is 2. The degree of the denominator, is 1, so we say there's no horizontal asymptote either. Okay, and then we say, okay, what's our x-intercept and our y-intercept? So we find that by just looking up here. What's left over is x divided by minus 2. So when x is 0, we get 0. And so our x and y-intercept are both 0, 0. All right, and then we draw a graph. So we have 1 point, 0, 0. We have a point of discontinuity at 2 and minus 1, and we connect the dots. And then we look at our domain and range. Our domain is x can't be 2, and our range is y can't be, just give me a second here, y can't be minus 1, because there's a hole there. All right. So here's another example. This one, all I did, very similar in terms of what the question's asking, except I changed this to a plus. And here's how that affects things. When you now factor, you get x times x plus 2 over minus 2 times x minus 2. Now there's nothing that cancels because these factors are not the same. So we say there's no point of discontinuity, but there is a vertical asymptote at x equals 2. All right? So that's where I'm getting that from. There's nothing that cancels, so there's no point of discontinuity. But this gives me a factor of x equals, or a root of x equals 2. Okay? So then we look at the horizontal asymptote, same thing, it's none because the numerator has a higher degree. And then we look for our x and y intercepts. Okay, so our x intercepts are when the numerator is 0. So you get x times x plus 2 is 0. So either you have 0 from this guy, right? Or you have minus 2, which is from this guy. So you have two options. You have two x-intercepts, 0, 0, and minus 2 and 0. And then the y-intercept, because you know the x-intercept 0, 0, you know the y-intercept is also 0, 0. So then we draw this graph. And what's different about this graph is we have a vertical asymptote, okay? So we draw that first. That's at x equals 2. Then we plot our points, okay? Our points are minus 2 and 0 and 0, 0. And that's all we know, right? Those are the only points we know. So then we look to connect the dots. And so we know that this is going to then have to come down through here and back up. And then this is where this gets a little funny. You have to come on the other side of the asymptote and say, what's going on over here, right? And you're wondering, well, where did you get this little weird thing? What I did is I noticed that there's no x-intercepts, okay? So it either has to, the possibilities are that it could do this, what I've drawn here, right? Kind of come down after a while, or it could come like this and then kind of go like that or something. It doesn't have a horizontal asymptote, so I know it's not approaching a flat line. So I have to decide which of these is it. And the way that I decide that is actually by taking a test point. So if I pick 3, let's say x equals 3, and I plug that into my function, which is back up here, so it's 3 times 3 plus 2, okay, divided by minus 2 times 3 plus 2, or 3 minus 2, sorry, right? Then what do you get? And we say, well, that's 5 times 3, so that's 15, and that's 5, or sorry, minus 2 times 1, because that's now a negative. So that gives me minus 2, so it's going to be a negative number. I don't really care that it's negative 7.5. I care that it's negative, okay, because the negative indicates then that it's down here. All right, and if it's down there, that means that it has to follow this pattern. We don't know how high this goes. Okay, we have no idea. It could come all the way up here and back down. It could kind of go up here for a while, flatten out for a while, and come back down. We don't know exactly what the behavior is there, but based on our information, we know that it's going to be negative. It's going to stay negative, okay? And you might be wondering, well, what about the possibility on this side that, hey, this could have gone like this, right? It could have come up through here, back down, and down like this. How do I know that it's doing what I drew there? And again, it's a test point. So you notice I have a point here that I've drawn in there. All I did was test 1. So what happens when I put 1 in? Okay, so I put 1 in there and I got 3 over 2. And that means that if it's 3 over 2 or 1.5, it's positive, right? So I drew it up here, and that then determines that this has to go like this, okay, instead of like this. So it can't go down because it's positive up here. So that's the idea. And there's more of them to do. There's certainly more questions you could do and certainly more examples that we can do, and we will do more of them in class, but that's the idea. So you do vertical asymptotes, horizontal asymptotes. If there is a horizontal asymptote, you will see, let me see if I can find an example that has, here's one that has a vertical asymptote. So let's just run through this quickly. So we first of all factor. That's what we did before. We talked about factoring, we talked about polynomial functions. We look to see if anything cancels out. So here, nothing canceled out, right? These two don't match those two. So I have two vertical asymptotes, one at 7 and one at minus 5. By horizontal asymptote, here's how you find a horizontal asymptote, okay? If the degrees are the same, then the horizontal asymptote is the quotient of the coefficients of the highest degree terms. And you might be saying, what does that mean? What you look at is just the degree is the same. They're both x squared. That's the highest degree. So the vertical asymptote is 3 divided by 1. That's what I'm saying. So you ignore all this stuff, and you just look at what's the coefficient here. And it's 3 over 1. So the horizontal asymptote is 3. Okay. However, it's a line. So you write y equals 3. And vertical asymptotes you write as x equals those values. That's why I'm writing them that way. It's actually an equation that's going to indicate a vertical line. All right. Then we look at the x-intercepts. The x-intercepts happen when these are 0. So those are -4 and 5/3. Okay, that's where I'm getting those from. And the y-intercept you can actually get from here. It's 20 divided by 35. Okay, and it comes to 4/7. So we have two vertical asymptotes, we have a y-intercept, we have an x-intercept, we actually have two of them, and we have a horizontal asymptote. Okay? And what we do is we take all that information and draw the graph based on that information. So here's what I know. Okay? I know the point here, that's an x-intercept. I know the point there is a y-intercept. I know this point as an x-intercept. And then these are my two vertical asymptotes. And this is my horizontal asymptote. Okay, so what has to happen is something has to happen over here. All right, this part has to have something, and the options are, if I change the color here to blue, there's two options. It either can go like I drawn it or down like this. But if it goes down like this, what's going to happen is it's going to have an x-intercept, and it doesn't. So that's how I know it's going like this. All right, and vertical asymptotes, they always go up to infinity. Then what happens here? Well, your options are, it could go down through here, right? But if it goes down here, goes down through this point, then we have a problem because we have a y-intercept that's positive, right? And so we can't go back up like this because that would mean the y-intercept is down here. So we say that's not possible. Excuse me. So that's why I draw this as I have it here. And then the same reasoning over here, I say it can't be down here because if it comes back up, it's got to hit the x-axis, and it doesn't. So that's how I know it goes this way. All right, and there's my sketch. And then from there, I can look at the domain. The domain is x can't be -5 or 7. Those are my two vertical asymptotes. The range, I don't know. The reason I say I don't know is because we don't know how high this portion goes. It could go up some more before it comes down, right? It's possible. It might, so in other words, this might be the highest point or it might not be. And because we don't know that, we can't state the range. So generally, you're just going to be asked to state the domain with these, all right? So that's how you draw rational functions. I'm going to leave it there. We'll do more examples in class. If you have any questions, you can bring them to class. But that's the concept of drawing a rational function.